Hello and welcome to episode 3 of this series on Coxeter groups. In this video we're going to talk about the weak order of Coxeter groups and the absolute order, as well as of course going through some cool examples and properties of these partial orderings. Let's get started. In the last episode we talked about the Brouillard order and how it could be characterized by multiplication by some element in your Coxeter group W, and then seeing how that affects the length. Okay, and at the end I teased whether this would be different if we restricted it to only be looking at what happens when you multiply by generators. And yes, it is different. And that is precisely the weak order. So let's go ahead and define that. So you've got your Coxeter group W and generating set S. Okay, so that's your Coxeter system. Okay, we define a relation which we will denote by a less than or equal sign sub R. Okay, where W1 is considered less than or equal to W2 in this weak order sense. Okay, and that means if we have W2 is equal to W1 multiplied by S1 up to SK. Okay, for K in there and SI in S. Okay, and we also have that the length of W1 times S1 up to SI is equal to the length of W1 plus I, for I between 0 and K. All right. So this is the right weak order, and okay, this is all very abstract, I appreciate. So what's it actually mean? Well, it's saying that if you can write W2 as W1 multiplied by some element, and you have the property that if you take this other element, okay, and truncate it at each generator, okay, at each SI, then the length of that is equal to the length of W1 plus the length of this thing, which, because it's made of generators, is I. So this is always a minimal decomposition. Okay. And I guess by extension, we would also have that the length of W2 is equal to the length of W1 plus K. Okay, because that's what the property says. Okay, there is a equivalent definition for the left weak order. Okay, which we denote by same less than or equal sign, but with an L for left. Okay, and that happens when we have W2 is equal to SK minus 1 down to S1 times W1, okay, for K in the natural numbers, and SI in S. And we also, of course, have here that this length property, okay, basically it's the same idea, but instead of multiplying on the left, you're multiplying on the right. So that's the left and right weak orders respectively. And you can go ahead and prove that they are both partial orderings. Okay, under the definition that I gave in the last video. Okay, but what's interesting is that we've been talking about the right weak order and the left weak order so far. Okay, and that is because they are distinct partial orderings, but the left and the right weak order are isomorphic under the map W is sent to W inverse. Okay, so I suppose the way of thinking about it is you've got a partial ordering going one way, and if you invert everything, it flips all of the partial orderings. So the Bruhat order had something called, it had the subword property, right? Okay, and that made things a lot easier when you're trying to find whether elements are like even comparable, let alone ordered in the Bruhat sense. Is there something similar for the weak order? Yes. Spoiler alert. Yes, there is. Okay, and it is the following. So you've got if you've got W1 and W2 in your Coxeter group W, okay, and you have that W1 is less than or equal in the right weak order to W2, okay, then W1 occurs as a prefix of W2. Okay, so what that means, so you can sort of picture, you can sort of understand where that comes from, because if you wrote W1, W1 as a series of generators in its minimal decomposition, okay, then you've got that W2 is equal to some sequence generators multiplied by some other sequence generators, but W1 itself, it does occur as a prefix of W2. Okay, and I believe that for the left weak order there is a similar property, but I think it refers to suffixes, so the end bit of the word. Okay, and I suppose we could call this the prefix property. Okay, and I should say that I might refer to just the weak order like on its own. I won't necessarily specify left or right. Usually I'll be referring to the right weak order if I do so. Okay, just to warn you. Okay. So the weak order is named as such because it is literally a weaker partial ordering than the Bruhat order. Okay, and that's exemplified by the proposition that if you've got W1 less than or equal to W2 in the Bruhat sense, then you must have W1 less than or equal to W2 in the weak order, in the weaker order sense. But if you've got W1 less than or equal to W2 in the weak sense, this does not imply that W1 is less than or equal to W2 in the Bruhat sense. So basically, you can go one way. If you've got something in the Bruhat order and they're ordered, then they will be ordered in that way for the weak order. But you can't go the other way. If you've got something ordered in the weak sense, you cannot necessarily say that it is ordered that way for the Bruhat order. Okay. The proof of that is, quite fairly elementary, I'd say. You know, you can convince yourself from the definition. Okay, let's have a look at a quick example. Okay, and what I think we'll do, we'll use the graphs of the week order, okay, which I will put up now. Okay, and I think I've also put up the graph that we drew for the Bruhat order. Okay, and you can see a very clear difference in structure. Okay, where the Bruhat order has all these sort of connections between sort of like every element. Okay, the weak order simply doesn't. And for me, this sort of demonstrates the weak sense, because if you try to imagine, you know, creating these graphs as a physical structure, so having nodes like as being like pins, and then, you know, rods, stiff rods connecting all of them in whichever in, you know, whichever order it is, then the Bruhat order will be quite rigid, quite a rigid structure, whereas the weak order would be a lot more malleable. It, you know, it'd be able to stretch and move around a lot more. Okay, and so that's sort of how I think about it. Okay, as with the Bruhat order, you do have some properties of the weak order, such as the existence of a maximal element, W naught. Okay, let's use a different sheet. Yeah. Okay, so maximal element W naught with W less than or equal in the right weak order to W naught for all W in W. Yep, that just about fits. Okay. We also have intervals and coverings that are defined in the same sort of way as they have been before. Okay. Let's Okay, we also have a length rule like we did for the Bruhat order, so W1 is less than or equal to W2 if and only if the length of W1 plus the length of W1 inverse times W2 equals the length of W2. Okay. There is again here there is a chain rule. Okay, so W1 equals x1 less than or equal to x2 less than or equal up to xn, and that's equal to, or x, well, I'll put xk in the paper. I may as well use the same notation here if I can. Okay, and here we also get that the length of xi is equal to the length of W1 plus I for I. Hold on, from starting at 1 going up to k. And this length sub property kind of thing is basically found when you apply the definition of the weak order to each individual partial ordering. That should have x2 there. Okay. And then finally, if you have got some element S, a generator in the descent set for W1 intersected with the descent set for W2, Okay, then W1 is less than or equal to W2 if and only if SW1 less than or equal to SW2. Okay, so what does this property tell us? Well, it basically says that if you've got some element S, okay, that makes W1 shorter and W2 shorter, okay, then you must also have that W1 less than or equal to W2 is true if and only if the this is sort of respected when you multiply by that generator S. Okay, I guess it's sort of an equivalence of the lifting property. Okay, we can have a quick look at intervals. So and coverings. You know, they're a little bit nicer than the Brouillard order in the sense that there isn't as much going on. Okay, so if you've got the same interval or the same what are they called? Not are they called boundaries? But the same elements that we looked at before. So S1 up to S1, S2, S1, S2. This interval is equal to S1, S1, S2, S1, S2, S1, and S1, S2, S1, S2. Okay. Okay. And the reason, so, you know, you can see that, you know, we are looking for all the elements, all the subwords of this element where S1 appears as a prefix. Okay, precisely the prefix property that we defined earlier. And then we've also got the covering that S1 is only covered by S1 and S1, S2. Okay. All right. So that's the sort of the properties of the weak order out of the way. Let's talk about automorphisms because we looked at automorphisms for Brouillard order. So let's see what things we've got for the weak order. Firstly, we acknowledge that multiplication by the maximal element, okay, and on both sides, on either side, okay, these are anti-automorphisms. Okay, so they flip the order. Okay, and similarly to the Brouillard order, if you conjugate by W naught, okay, by this maximal element, then this is a normal automorphism. Okay. Okay. But there's another one that I would argue is a little bit more interesting. Okay, and this is a subset automorphism that is unique to the weak order in Coxeter groups, that is. Okay, so this says if we let W1 and W2 be in our Coxeter group W, okay, and we've got W1 less than or equal to W2 in the right weak order, then the interval W1 to W2 is isomorphic to the interval starting at the identity, okay, and going to W1, that should be W1 inverse W2. Okay, now the proof's a little bit abstract, bit beyond the scope of the video series that we're doing here. Okay, but it is really interesting that, in a sense, you can take some interval, pick it up, and map it to be able to start the identity. And if you've got something, an interval, and it starts at the identity, it's a lot easier to work with, I would say. Okay, let's have a look at an example of this in action. Okay, let's have a look at S5. Okay, and we'll let W1 equal 1, 2, 4, 5, 3, and W2 equal 1, 2, 4, 3, 5. Okay. So we can check by the northwest criterion that W1 is less than or equal to W2 in the right weak order. In fact, well, the northwest criterion it tells us what's less than in the Brouillard sense, but because of the proposition that we mentioned earlier, okay, if you've got Brouillard ordering, you've also got weak ordering. Okay. And so the proposition that we discussed just now, okay, tells us that the interval from W1 to W2 is isomorphic to the interval where you start at the identity, and we have W1 inverse going up to W1 inverse W2. Okay, so let's work out what this interval is. Okay, so first of all, we'll work out what W1 inverse times W2 is. So to find an inverse in cyclic notation, you just reverse the notation, the cycle. So we have 3, 5, 4, 2, 1 multiplied by 1, 2, 4, 3, 5. And that gives us, well, 1 goes to 2, 2 goes to 1, so 1 is on its own. 2 goes to 4, 4 goes to 2, so 2 is on its own. 3 goes to 5, 5 goes to 4. 4 goes to 3, 3 goes to 5. And then we will double check. 5 goes to 1, 1 goes to 3. Okay. So, yeah, we end up with this. So, to simplify, okay, we end up with this interval. Okay, and that is equal to the identity, the cycle 3, 4, and the cycle 3, 4, 5. Okay, then here's the interesting thing. So we can multiply now by W1, okay, to find what the interval W1, W2 be. Okay, and that is the following. Okay, 1, 2, 4, 5, 3, which we knew. Okay, W1 multiplied by 3, 4 gives us 1, 2, 4, and then 3, 5. And then we get the third cycle is W2, which is 1, 2, 4, 3, 5. Okay, so E goes to W1, 3, 4 goes to 1, 2, 4, 3, 5, and then 3, 4, 5 goes to 1, 2, 4, 3, 5. And let's close that set off. You can't see it because of the camera, but whatever. It is closed, yeah, look. Okay. Okay, that's everything that I wanted to talk about on the weak order. Let's move on now to talk about the absolute order, because the Bruja and the weak orders both rely upon S being a minimal generating set. Okay, and I wonder, when I was doing my masters, I did wonder, what if you change your generating set? Do you get anything interesting happening there? And I discovered that Armstrong, I don't know their first name, but a link to that their paper that they wrote is in the bibliography of my paper, which you can find in the description. But they asked the question, what if we loosen the generating set to be any reflection? And what happens there is that you end up with a completely different partial ordering on your Coxeter group. Okay, and the partial ordering sort of takes properties of both the Bruja and the weak order, which I think this is pretty cool. So let's go ahead and have a look at that. But first of all, we should define what's called the dual Coxeter system. So that is WT. Okay, so W is your Coxeter group, and then T is the set of all reflections. Okay, which are basically conjugations, but yeah. Okay, so we are setting our Coxeter group W to be generated by all reflections in W. Okay, so despite its name, okay, it's called the dual Coxeter system. Okay, but despite it having the word Coxeter system in its name, it isn't a true Coxeter system. Okay, because you can classify all Coxeter systems. Okay, and sort of based on their generators and stuff like that. Okay, but WT doesn't always show up. A good example is in S3, okay, where the generating set, the minimal set would be adjacent transpositions, so 1, 2, and 2, 3. But if you include the reflection 1, 3 in that, then you don't have a Coxeter system, because that generating set doesn't appear in the classification. You can read about it in my paper, and I think there is a link to a book where they talk about it in a little bit more detail. Okay, so you might be wondering here, what's the point if it's not a true Coxeter system? Why are we going to look at it? Well, one benefit of using the set of all reflections as your generating set is the non-uniqueness, which, yeah, that's a word. I'm going with it. Okay, the non-uniqueness of elements kind of becomes helpful, and we will see an example of this a little bit later. But now that we have got our dual system, I think we should redefine the length function for WT. Okay, because you've got more generators. Okay, so you've got to change the definition slightly. So define a length function LT. Okay, going from your Coxeter group W to the natural numbers. Okay, and so this is with respect to T, the reflection set. Okay, and this is the minimal number of generators required to express W in W. Okay, and this is known as the absolute length. Okay, and it's very important here, I've written generators. In this case, under the absolute length, generators refers to reflections. Okay. Okay. An interesting thing to note, well, first of all, words, subwords, decompositions, and all that are all defined in the same way that you would expect them to be. Okay. But an interesting thing is that because reflections are conjugations, okay, let's put that up here. Okay, we have the property that the length is unaffected by conjugation. Okay, and that is conjugation by any element. All right, now that, you know, that's pretty interesting, right? You also get that the length function is unaffected by inverting, which, I mean, okay, this is sort of given in any partial ordering under Coxeter systems, because to find the inverse you just reverse the elements. But okay, so the length doesn't change. Okay, but for the length to be unaffected by conjugation, you know, that's quite a bit different. And the way you go about proving that is you write each generator as a sort of a sub-conjugation or something. I don't know. It's a bit weird to explain. You can have a look at the proof in my paper, which is in the description below. Okay, but now that we've got a length function, we can go ahead and define the absolute order. Okay, and that is given by the following. Okay, so we have a relation less than or equal sub t. Okay, and we have W1 less than or equal sub t to W2. If and only if the length of W2 is equal to the length of W1 plus the length of W1 inverse W2. Okay, so that's the absolute order, and that sort of might look familiar because we mentioned a property of this sort in the weak order, and this comes down to the thing that I was saying about it, the absolute order sort of taking bits of the weak order and the Brouwer order. Okay, and you know, you can go ahead and check that this is a partial ordering, you know, go for it. But let's start looking at some examples and properties. The first property that I'd like to mention, okay, is to do with something called a Hasse diagram. Okay, and the Hasse diagram is a directed graph. Okay, HWT. Okay, where connections are shown if and only if X is covered by Y in the absolute sense. Okay, and and what's interesting about the Hasse diagram, okay, is that the Hess diagram is isomorphic to the Cayley graph, both under T. Okay, so basically, all the coverings, okay, in the absolute order give you precisely the Cayley graph. If you worked with reflections, okay, and I'll just quickly put up a picture of Hess diagrams for the Coxeter group D6 and S3. Okay, I did consider using S5, but because permutation groups grow factorially, if I used S5, I'd have to draw 120, 5 factorial nodes, and then all of the connections between them under the absolute order, which frankly I did not want to do. Okay, but you can see just as clearly, what happens under the absolute order with S3. Okay, and one thing to note here is the absence of a unique maximal element. There are multiple maximal elements, and the reason for that, okay, and you can kind of see the logic here, because you can have multiple versions of the same element, in the sense, you can have an element generated by different sets of generators. Yeah, that makes sense. Okay, and so you lose that uniqueness of maximal elements. Okay. Okay. So I'm now quickly going to pivot over to root systems. Okay, and that is just so. If you're unfamiliar with root systems, don't worry. Okay, I define them a little bit more in depth in my paper, but basically they are sets of vectors alpha, okay, that are invariant under W. So what does that mean? Okay, so if you've got a root in your root system phi, okay, then you have that, if you act on phi under W, so W phi, it stays isomorphic to phi. Okay, basically. So yeah, if you've got like a bunch of roots, it's sort of like if you're familiar with roots of unity. Okay, and that's partly why we say root systems, because it comes down to roots of polynomials in a way. Okay, but if you're familiar with roots of unity, you'll know that if you multiply any two roots of unity together, you get another root of unity. Okay, and it's the same sort of deal here. If you multiply under W, if you multiply any two roots together, you stay in phi. But if you act upon phi by W, okay, then you stay in your root system. And what does that mean? Well, it just means, okay, that if you've got a root alpha in phi, okay, then T alpha is the associated reflection in the hyperplane orthogonal to alpha. Okay, so what does that mean? Okay, what does that mean? It means that if you have a root system, which is a bunch of vectors, okay, and you've got a root alpha, you take the hyperplane orthogonal to it, okay, to alpha, and take that reflection. That is precisely T alpha, okay, and the reason that I am mentioning this here, okay, is that if you have got a T word, W equal to T alpha 1, T alpha 2, all the way up to T alpha n, okay, then we can say that this is reduced. Okay, so it's got its minimal decomposition if and only if the set alpha 1 up to alpha n is linearly independent. Okay, so what does that mean? It means that you can't take a number of these and create one of the other roots. Okay, so the proof of that isn't too bad. Okay, you can have a look at that in my paper below. Okay, but a couple of corollaries of this tell us that, firstly, no reflection may be repeated, okay, at all in the absolute order, okay, or rather in our dual system, I guess. Okay, and you can sort of, again, you can convince yourself that this is true, because if you're going through a series of reflections and then you reflect once, do a bunch of others, and then reflect back, it is sort of like, well, why did I do the same thing twice? But what's interesting here is that it is any reflection. Okay, it's not just consecutive ones, which it would be for a normal Coxeter system. Okay. We also get that where we don't have maximal element, okay, but we do have maximal length. So we will always have the length of W with respect to T is always less than or equal to n, where n is the rank of T. Okay, so in other words, it's the number of generators. And again, convincing yourself isn't too difficult, because if no reflection may be repeated, okay, what does that mean? Well, in terms of maximal ones, once you've used up all the reflections, you haven't got any more, so that is your maximal length. Simples. Okay. Interesting thing about the absolute order is that it is achiral. Okay. And that's because that's to do with conjugation being invariant. Okay. So we saw that the absolute order had its definition had a property that was similar to one in the weak order. Okay, but the absolute order also has a subword property like the Brouillard order. Okay, but to get there, we first have to sort of consider some lemmas. So we have the shifting lemma. Okay, and the shifting lemma states that if W equals T1 up to Tn, or Tr actually I use, okay, in your Coxeter group W, okay, and this is reduced, okay, then you also get W1 equal T1, T2 up to Ti minus 2 Ti, Ti minus 1, Ti, Ti plus 1 Tr. Don't worry, I will start talking again in a moment. Okay, and T2 up to Ti minus 1 Ti. Okay, so these are also reduced expressions for W. Okay, so it comes. So I did sort of tease this earlier with the non-uniqueness part. Okay, and this is precisely how you get other um, other reduced expressions. Okay, I'm not going to prove it here because effort. Okay, but you can have a look at the proof in my paper. Okay, but what this does is that first of all it shows that you can use the shifting lemma to prove that there is no difference between the left and right absolute order. Okay, in other words, it is achiral. Okay, but a corollary, okay, is of the shifting lemma is the subword property for T words. Okay, and that is that if you've got W1 less than or equal to W2, then this is true if and only if W1 occurs as an arbitrary, just about, arbitrary subword of some reduced form T word for W2. Okay, so what's that saying? Well, it's saying that you have a subword property, but because of non-uniqueness, you need to sort of consider that you might have to use the shifting lemma to shift some elements around, hence the name. Okay, but the beauty is that these are still reduced T words. These are still reduced. Okay, and so you can still use this sort of subword property. I just think it's nice. Okay, I just think I like it. Okay, it's a nice property. Okay, now that we've covered all of that, let's see this in action. Okay, so let's have a look at S5. Okay, and its reflection set T is the set of all transpositions. Okay, so this is 1, 2, 1, 3, up to 4, 5. Okay, yep, that's fine. Okay, so let's take again W equal to 1, 2, oh, no, 1, 2, 5, 4, 3, as it was earlier. Okay, we can decompose that into 1, 2, 2, 5, 4, 5, 3, 4. Okay, so I've just sort of pairwise split this up. Okay, and I'm going to quickly, well, okay, I'm going to tell you that this is reduced. Okay, I proved that it is using matrix representation theory in my paper below. You can have a look at that. Okay, I'm not going to do it here because it's a bit long, but you can either trust me or look there. Okay, but let's have a look at the shifting lemma on W. Okay, and I'm going to transfer to a different color. I'm going to use blue for this. Okay, so if we so first of all, let's have T1 equal to 1, 2, T2 equal to 2, 5, T3 equal 4, 5, and T4, 3, 4. So we have W equals T1, T2, T3, T4. Okay, and let's take I to be 2. Okay, I in the sense that we were using the letter I up here. Okay, so we get that W equals T2, T2 inverse, T1, T2, T3, T4. Okay, and if you work that out, you get 2, 5, 1, 5, 4, 5, and 3, 4. And we also have that W equals T1, T2, T3, T2 inverse, T2, T4, and that is 1, 2, 2, 4, 2, 5, 3, 4. Okay, and if you work out, if you calculate the simpler, the full sort of cycle stuff here. Okay, if you work these out, you will end up with W. You can just trust me on that, and you can use matrix representation to verify that these are both reduced as well. Okay, so that's nice. And the great thing about the shifting lemma is that you can, shift everything around, move things along, and what that does is it allows you to find minimal decompositions if you don't necessarily already have them. Okay, so yeah, that's nice. So finally, I would like to have a look at something called the Carreras complement. Okay, and this is a function on W. Okay, that looks like this. So you have W1 and W2 in W. Okay, we define a function K, W1, W2. Okay, so lower and upper, going from W to W. Okay, and this is defined by K, W1, W2 of some element W equal to W1, W inverse W2. Okay, Then, if we have W1 less than or equal to W2, okay, then the following hold. First of all, we have that KW1, W2 is an anti-automorphism of the interval W1, W2 under T, and for all x in W1, W2, the interval, we have that the length of the Carrera's complement of x is precisely equal to the length, that should have a t there, okay, of W1 plus the length of W2 minus the length of x. Okay, so so basically, if you want to find the length of this thing here, you just have to find the lengths of all of those, and then add, subtract, and add like that. I like, it's a lovely, cool little property. Okay, an interesting. Well, okay, I should say, I do prove this in my paper, link in the description below, but again, effort here, I don't want to put it in, but it looks quite complicated when you have a look in the paper, but it's not so bad. Okay, it's just sort of going through the motions with, rewriting elements in certain ways and using the shifting lemma here and there, stuff like that. It's not so bad. Okay, a corollary of regarding the Carrera's complement, okay, is that for all W1 that is okay, so if you've got this chain, so basically x and y are in the interval W1, W2, okay, then taking the Carrera's complement of the following, okay, you end up with this, right? Okay, and that looks confusing, but what it's saying is that well, let's work this out quickly. You have W1 x inverse y less than or equal to, with regards to t, W1 x inverse W2. Okay, so yeah, thought so. Basically, it doesn't affect the absolute order. Okay, so you end up with an anti-automorphism of the interval, okay, under the Carrera's complement. But if you take elements in that interval and you put them in the Carrera's complement in this sense, okay, you don't affect the order. And the proof comes down to basically using this you use this because that's a property of the Carrera's complement, okay, and you can deduce that you do indeed have this, okay. Okay, let's have a look at an example of the Carreras complement on S5. Okay, so let's take, and we'll go back to blue again. Okay, let's take W1 equal to 1, 2. Okay, W2 equal to 1, 2, 5, 4, 3, which we used earlier. Okay, which we saw is equal to 1, 2, 2, 4, 2, 5, and 3, 4. Okay, we'll also take x equal to 1, 2, 4, and which can be rewritten as 1, 2, 2, 4. Okay, and y equal to 1, 2, 4, 3, which can be written as 1, 2, 2, 4, 3, 4. Okay. Okay, so let's have a look at this. So clearly we definitely have W1 less than or equal to no, X less than or equal to Y less than or equal to W2. Okay, so X and Y are in the interval between W1 and W2. Okay, let's check whether we get the following. Okay, so for this, I know that in the definition of this property that we were looking at, I had the x's and y's and stuff in a different place. This is the same thing, just reworked a bit to work a bit nicer with with the elements we're dealing with here. Okay, so first of all we get k w1 w2 y, and that is equal to 1, 2, 3, 4. I might speed this bit up. Five. Okay, so it's not the clearest. I mean, because I'm using a Sharpie, but the point still stands that what you end up with, okay, is you end up with KW1, W2 of Y is 1, 2, 2, 5, and that definitely is less than 1, 2, 2, 5, 3, 4, or KW1, W2 of X. Okay, so basically here the Carreras complement works. Okay, and one final thing. Okay, one final thing is that so we had that the weak order had this property of W1 W2 in the right weak order, this interval is equal to the identity up to W1 inverse W2. Okay, and I conjecture, okay, that there is a similar property with W1 W2 under T being isomorphic to E W1 inverse W2 under T. Now, I like I said, it's a conjecture. I haven't proven it. I haven't, you know, gone into any more detail. It's just a thought. It feels right. In fact, I think that it will be a little. I'm not sure if it would be weaker or stronger. Depends on how you see things. Okay, but I reckon that you will what you'd end up with is here you'd have a bunch of isomorphic intervals starting at the identity, like, you know, they would all, you would have a big chain of them. Not a chain, like sort of like a I'm not see, yeah, I honestly I am not sure. That's why it's a conjecture. Okay, and I invite you, you know, if you have a think about it and you manage to prove it or get somewhere with this, then yeah, by all means, drop a link, drop a thing in the comments below. Otherwise, that is everything that I want to talk to about the weak orders and absolute orders. Okay, if you want to read my project, what I wrote for my master's degree, there is a link to the paper in the description below. Hope you've enjoyed the video. If you did, hit like, hit subscribe, do all the stuff, and I'll catch you in the next one.